All right. Hope everyone did well in the midterm. Um, yeah. So right now we're going into lesson 11. It's going to be focusing mainly on chi-squared, uh, statistics, stuff like that. So without further ado, we'll get right into it. And I will warn you guys, it's a very, very quick lesson. So I won't keep you away from all that snow that we've been getting and stuff like that. So let's just get right into it. So, all right. So first off, the goodness of fit test. Um, just some stuff about it. So it can be conducted when there is one categorical variable with more than two levels. Basically, what that's saying is you can use it to compare proportions when there are more than two independent groups. You can use it if the expected counts are all at least above five or five and above. So you can use the chi-square test. And so the way you calculate that is the expected count equals n times p sub I. So basically, n is the sample size, and p sub I is the hypothesized proportion for the group. If you expect a count that is not at least five, then you have to use randomization testing. So the goodness of fit test, basically, what you can do with it is compare observed counts to expected counts. So the observed counts are the number of cases in the sample of each group, and the expected counts are computed given that the null hypothesis is true, and this will be the number of cases that we would expect to see if the null hypothesis were true. And you can see right over here, this is how you calculate the chi-squared stuff. So x squared is a chi-statistic. This symbol right here is basically saying you sum the observed score minus the expected score squared divided by the expected score, and that's how you get your chi-square. All right, so for the chi-square distribution, it varies depending on your degrees of freedom. And so to calculate it for the chi-square, it's degrees of freedom equals number of groups minus one. And so you find the p-value. We want to find it using the area that's under the chi-square distribution to the right of our test statistic. And that's how you find the p-value. All right, so when it comes to hypothesis testing for the chi-square with the goodness of fit test, I will say that just because there's goodness of fit and it's also independent. So first off, check your assumptions and hypotheses. So the null hypothesis, null hypothesis contains the equalities, and the alternative, there's going to be at least one population proportion that is not as specified as the null. So basically what they're saying is the null is going to say they're all equal, and the alternative is going to say one of them isn't equal. And then your assumptions is that all expected counts must be at least five. And the test statistic is the exact same as the chi-square that we saw earlier, exact same equation, ba-boom. So just continue with it. It's the exact same steps that you've seen before. P-value, you want to construct the degrees of freedom equal to number of groups minus one, like I said before. P's values under that distribution to the right of the test statistic. It's the exact same deal as before. If P is less than or equal to alpha, you reject it. And if P is greater than alpha, you fail to reject it. And then you just state that in a real world conclusion. So chi-square test of independence, this is the other one I said, is really used for testing the relationship between two categorical variables. So it computes the expected values for cells in a two-way contingency table under the assumption that the two variables are independent. And again, you just use the same five-step hypothesis procedure. So when it comes to hypothesis testing, the assumptions are that all counts must be at least five. Again, same as before. And that the sample is randomly drawn from the population. So your null hypothesis is going to be that there's no relationship between the variables, and the alternative hypothesis is that there is a relationship between the variables. So test statistic, again, voila, same as before. Then you also have this expected cell frequencies where you can literally calculate in the table where it's going to be the row total times the column total divided by the overall sample size. And so I have a question about this later that you can see and we'll go through. But just, remember this equation. And then, so for p-value, you have to keep in mind that for this, the degrees of freedom is different. So to calculate that, it's the number of rows minus one multiplied by the number of columns minus 1. And then, you still know the rest about your decision and then stating that real-world conclusion. All right, so then one more thing, we have relative risk. So way back when, we went over risk, and we basically said that risk is often used to describe the probability of an event occurring. So an example of this is with the flu. If 0.45 out of 100, if you have like 0.45 out of 1, probably of it occurring divided by the total population, then you'd have 0.45. So then you'd say that the child has a risk of 45 out of 100, or 0.45. But what relative risk does is it compares the risk of an outcome in two different groups. So basically it's like group 1 divided by group 2. So the example of this that I said, well, take for instance that the adult risk is only 0.1 instead of 0.45. So then it would be 0.45 divided by 0.1. So it would be a child is 4.5 times more likely than an adult to get the flu. And then you'd see it kind of written as your first group is however many times that you calculated more likely than the second group to get whatever is your the outcome that you're saying. So, again, in this scenario, it'd be children are 4.5 times more likely than adults to get the flu. So, yep. And then with that, we're into review number 1. So I'll give you guys a little bit of time to answer this. What are the degrees of freedom that a 2x4 chi-square test of independence has? So I'll leave you guys to it. All right, so we're going to go over it. So the correct answer is D, 3. You're basically taking the equation that we saw before, so it's number of rows minus number of columns. In this case, it would be 2 minus 1 times 4 minus 1, so you just get 3. So, all right, good job. Next up, so given the following table, how many non-smoking females would you expect to obtain a random sample of 1,033 people? So all the data is right in here. And again, I'll just give you guys a few minutes to answer this, and then we'll go over it. All right, so we're gonna go over it. I will say that the table's not on the second page just so I could write it out a little bit better, but yeah. So basically to calculate this, you get the total row value times the total column value. So since we're looking at non-smoking, that's the total of that is 720. And since we're looking at female, the total of that is 589. So 589 times 720, and then we're dividing it by the total, which is 1,033. And when you put all that in together, you get 410, which is different than the actual the actual one that they gave us in the table of 418. So, and yeah, if you rounded it, it would be a little bit different. I just included this raw data. I could have technically put it out a few more decimal places, or I could have also rounded up. I just wanted to go with the easiest like the whole number that came up. So sorry if that threw you off a little bit, guys, but that's just what I put. So yeah, and I think we got one more question. Yep. So this one is taken directly from a previous quiz. So I'll let you guys go over it. It shouldn't be too hard, and then we'll go over it. All right, so just gonna go over it. So it's on the next slide, so I'm just gonna really go over it here. So it says at the alpha level of 0.05, it's asking what we should do with the null, and then it's also asking, is there evidence that the spinner is unfair? So you can see here that's given to us that the p-value is less than 0.05, is actually 0.0012. So we can reject null, and then there is sufficient evidence to say that the spinner is unfair. Yeah, they just gave you a ton of stuff that might make you go look in another direction, stuff like that. But as I said, this was taken directly from a quiz. Might be something that could appear on the final or something like that. So there's that. And then, yep, here it is written out by me. And with that, that's the end. So I hope everyone has a great Thanksgiving break. Should be nice family time. Hopefully, you guys can actually go and enjoy it. I hope everyone stays safe in this weather. It's, horrible. I know I've certainly seen my fair share of accidents today, and I've heard of commutes that have been, going on for hours. So just everyone, please stay safe. And also, my next review isn't going to be until November 29th. We get Thanksgiving off, so I hope everyone can enjoy it. Hopefully take a little bit of time off stat, and I'll see you guys in about 2 weeks.